In this video, I'll explain what an antiderivative is and show you how to compute antiderivatives of polynomials. First, what is an antiderivative? A function, capital F, is an antiderivative of a function, little f, if the derivative of capital F is equal to little f. I'll point out that it's common to use a capital letter to denote the antiderivative of a function. Now, what does this definition mean? Here is an example. What if we want to find an antiderivative for the function f of x equals 2x cubed minus 4 over x to the 8th plus pi? That definition tells us that an antiderivative for little f of x is a function, big F of x, where the derivative of big F of x is little f of x. Now would be a good moment to pause the video to see if you can find a function with this derivative. Were you able to find one? Let's work through this example. Now, finding the antiderivative of little f will be easier if we break this down into pieces. Let's just look at the first term of f of x. Our new goal will be to find a function whose derivative is just the first piece of f of x. We'll call this first piece g of x. And, to keep things simple, let's just focus on finding an antiderivative of x cubed. Our method is to guess a function, capital G. Since we know that the derivative of a fourth-degree polynomial is a third-degree polynomial, for our first attempt we might guess x to the fourth as an antiderivative of x cubed. Next, we'll check to see if our guess is correct. To do this, we'll compute the derivative of x to the fourth using the power rule. We get 4x cubed. And then we want to compare this to little g of x. And they're not equal. So this first guess at an antiderivative is not correct. But it was close. It was just off by the coefficient of 4. Let's make another guess. This time, let's try 1/4 of x to the 4. We'll check by computing its derivative. The derivative of this new capital G is equal to x cubed, which is our little g. So, an antiderivative for little g of x is 1/4 x to the 4th, because the derivative of capital G is little g. Going back to our main goal of finding an antiderivative for little f of x, since the first term of little f is 2 times little g, then we would anticipate that the first term of the antiderivative for f is twice what we just got for capital G. So, let's try 1/2 x to the 4th. To check, we take the derivative of 1/2 x to the 4th. This derivative is 2x cubed, and we can see that this is equal to our first term of little f. Now let's look at how to find the antiderivative for the second term of little f. Let's simplify this a bit and attempt to find a function whose derivative is just positive 1 over x to the 8th. It might be easier to rewrite this fraction using a negative exponent. Before we make the first attempt at an antiderivative for h, let's go back to g. You might have noticed, for g we divided by the new power of x when doing the antiderivative. Let's try the same thing for h. For our first guess, let's use x to the power of -9 and multiply by 1 over -9. To check our guess, we compute the derivative of capital H and get -9 times 1 over -9 times x to the -10, which simplifies to just x to the -10. If we compare this to little h of x, we see that they're not equal, so this guess didn't work. Now, if we look at the exponents for big H and h prime, when we use the power rule, we subtracted 1 from the exponent. For x to the -8, we need an antiderivative, so let's try adding 1 to the exponent. So, for our second guess, let's add 1 to -8 to get -7, and multiply by 1 over -7. To check our guess, we compute the derivative of capital H, and, after simplifying, we get x to the -8, and this is equal to little h. So, an antiderivative for little h of x is -1/7 x to the -7, because the derivative of capital H is lowercase h. Since the second term of f is -4 times as much as lowercase h, then we would anticipate that the antiderivative for f's second term is -4 times as much as what we just got for h. So we'll use -4/7 x to the -7. Now, to check, we take the derivative of -4/7 x to the -7. And we verify that this is the derivative of the second term of little f. Now let's figure out an antiderivative for the last term of little f. So we want to find a function whose derivative is pi. This function must be pi times x. So an antiderivative for the function that is pi is capital K of x equals pi times x, because the derivative of capital K is little k. We can add this to our antiderivative formula for f. And now capital F is an antiderivative of little f, because the derivative of capital F equals little f. If you look at the antiderivatives for the first two terms of f, you might have noticed a pattern. In both cases, we were computing antiderivatives of x to a power, and the antiderivatives involved adding 1 to the power and dividing by the new power. This pattern suggests a rule for antiderivatives. We'll use capital F to denote an antiderivative of the function little f. First, if we have a function of the form x to some power p, an antiderivative is given by 1 over p plus 1 times x to the p plus 1. Note, though, this only makes sense if we are not dividing by 0. So the denominator, p plus 1, cannot equal 0, or equivalently, p cannot equal -1. This is often called the power rule for antiderivatives. An antiderivative of pi can be done using the power rule using p equals 0, but often finding the antiderivative of pi is viewed as a special case where a function is equal to a constant. In this case, an antiderivative of the constant function is the constant times x. Now, both of these rules work because if you differentiate capital F, you get little f. But these rules are not entirely precise. To see why, let's go back to our original task. For this problem, we found an antiderivative of little f of x. Can we find another function whose derivative is little f? Now would be a good moment to pause the video and attempt to answer the question. Did you find another function? It turns out that there are many other functions that are antiderivatives of little f. For example, start with the same capital F as before, and then add 17. We can check by computing the derivative of capital F, and we get little f, because the derivative of 17 is 0. There is nothing special about 17. So other antiderivatives of little f are capital F of x plus any constant c, where c is any real number. This leads to some adjustments to our antiderivative rules. Let capital F denote an antiderivative, and c denote any real number. To each of the formulas, we now add a plus c, creating a more general antiderivative. Both of these rules work because if you differentiate capital F, even with the plus c, you get little f.